All right, guys, we are going to talk about a couple of problems here that have to do with centripetal acceleration in order to kind of better understand the process. And this problem that I have here, I've used in a few years, talks about the F-22 Raptor, which is currently, I believe, the newest tech, although I don't know if I've looked in the past couple of years, so it might have less. But let's look at a few things. Number one, its mass when completely empty is about 19,000 kilograms. It has a maximum takeoff weight of 38,000 kilograms. And you can see in this next line, the difference, of course, there being fuel. With our conversations, you can recognize then that there's kind of a give and take when choosing how much fuel to put in the jet. It's not like you and I, when we go to the gas station, probably just fill up the tank to the top, because the more mass of fuel you, of course, put in the jet, the more mass it has, and therefore the more difficult it has to handle. So there's a give and take. But you can see from the next line here, it says, we're going to say that the fuel makes it around 30,000 kilograms when we're looking at this particular thing. Okay. It has a maximum speed of 1,500 miles an hour, roughly 750-ish, 700 meters per second, which is close to Mach 2, which you'll see down here in just a second. But in order to dogfight, they actually slow down to a maximum speed of 0.7 times the Mach. Mach 1 is just the speed of sound. So, of course, we'll have to do some stuff here to find the exact speed that is, and it's obviously going to speed up and slow down. But we're going to say if it's at this speed and this particular mass, find the radius a fighter would take to pull a 7G vertical loop. Now, we haven't talked very much about G's, but a G is literally just a measurement of acceleration. It is not any type of different force whatsoever. So when this says a 7G vertical pull, essentially that's an acceleration of 9.8 times 7. The reason why we do this is because everybody has a good understanding of how much force it takes with 1G. A G would be your weight. And now this is different for each person because obviously their weight is different. But whatever the force that it takes, your weight, okay, that you feel every day, is the force it takes to pull 1G. So if I then said that a 200-pound person, 1G, has to pull a 7G, 7 the amount times the amount of acceleration pull, you can then very quickly in your head go, well, 7 times 200, that means you have to put 1,400 pounds of force on that person in order to pull that off. And now you can go, oh, that's quite a bit of weight. Anyway, let's get to the problem and how to solve it. It actually shouldn't be too hard here. Let's go ahead and pull up the camera. Hello. So we said the mass of the plane is going to be about 30,000 kilograms. And the speed of plane, you'll notice I put a T on there, is 0.7 times Mach, or 343 meters per second. The question is, what radius would you go in order to pull an acceleration of 7 Gs, which, let's just go ahead and knock that out real fast. 7 times 9.8 would be 68.6 meters per second squared. And the speed that they're traveling, 0.7 times 343, is 240.1 meters per second. All right. So since we have acceleration, we know how much change in velocity over change in time we're going to get. And since that is specifically centripetal, since it says we're going in a turn, let's go ahead and draw a picture here. And we're going in, I believe, a vertical turn. Excuse me. I believe it says vertical. Yeah. We know that this acceleration can be seen as vt squared over r. Now, I've talked quite a bit at length about how these two do not make this happen, but they ask how much is going to happen. So really what we say here is if we have this amount of acceleration that is provided by a sum of forces, and you're going this fast, what radius essentially can we pull off? And that's just going to be a simple radius, just this around, radius is equal to vt squared over, acceleration. So that's going to be 240.1 meters per second squared divided by an acceleration of 68.6 meters per second squared. 240 squared divided by 68.6, and you get 840.4 meters. Now, if you ever run track, I always like to put these things in perspective. Of course, around the full track is 400 meters, 4 laps to get you a mile. So, of course, the 800-meter dash, about half a mile. So this is about a half a mile radius that a plane has to fly in, and that's pulling 7 Gs. It seems kind of crazy until you consider they're going 70% the speed of sound. There's a bell. Anyway, so there's part A. Now, part B in this problem asks you to draw a force diagram at the bottom and the top. I'm going to close the door real fast. There are 2 types of force diagrams that you potentially want to look at. Okay, the first force diagram is definitely going to be the easiest. It is just a net force diagram. We don't usually focus on this too much because of how simplistic it is, but maybe that gets us into trouble sometimes. And this is the net force in Newton's second law, which basically says, hey, the direction of acceleration is going to be the direction of force. So if I was at the bottom and the top, let's go ahead and draw this plane kind of upside down-ish here, according to the way I drew it. The net force should be, as we know, perpendicular to the velocity, but also, as you can see in this particular case, acceleration is towards the center, and so your force diagram would simply be towards the center. That's it. Now that is good to know, but it is probably not the most common way we need to look at this. So let's talk about the second type of force diagram, which addresses the individual forces that are happening in this particular case. Now, if you look at the bottom, of course, we know that this is going to have gravity, straight down. The other force that's on it acts extraordinarily similar to force normal, but it's called force lift. Essentially, if you've got your wings, air comes underneath and blows straight up. And the reason it acts similar to force normal is that force lift is going to go perpendicular to the wings, which are usually obviously flat, so usually it's going straight up. Okay? Of course, if the wings tilt, which may come into play in a later problem, then if they're tilting, that would be a force normal going still perpendicular to the wings. Now, in this particular case, we have force gravity down, and we should have force lift up, and this is the mistake that people usually make. They just make them equal, and that's fine. But Newton's first law says if they're equal, this velocity should stay constant, both in magnitude and in direction. We also see from here that there needs to be a net force, an extra amount up. So it would make sense then that force lift would be much bigger than force gravity. How much bigger? Well, force gravity needs to be equaled out by this much force lift, and this extra amount over here is the net force. Okay? So in this case, gravity is hurting it going in a circle, which is why if you were to go in a vertical loop, you will probably feel the most amount of force on you at the bottom of the loop. Now up here on the top, we still have force gravity coming down, but we'll see in this case that actually force lift was still necessary, which you'll see in just a minute. But force gravity is helping some of forces, so force lift is going to go down. So there are your force diagrams. This is probably, if it doesn't say anything specific about what type of force diagram, this is the one that you probably want. But of course, these you want to consider because you need to see that, hey, we need to have extra in this particular case, and obviously it's going to help here. Now, how did I know that you're still going to need force lift? Because you are pulling a 7G turn. Okay? Force gravity causes 1G. This extra amount of force would cancel that, so actually this extra force here is probably going to be 7 times what this guy normally is. Okay? Because we have to counter out that. So this total force lift would be 7 force of gravities plus this extra one, or 8 times what force gravity usually is. Up here, again, we need to pull an acceleration that is a 7g turn. I'm getting 1g out of force of gravity. So force lift needs to provide the extra 6. So it's going to be less push of force lift in this case, but still going to be necessary to pull that particular one off. Okay, final question here is part C. So this was part B, the force diagram. Part C says, find the force lift that would cause this acceleration at the bottom. This should be relatively easy because we just do Newton's second law. Sum of forces equals mass times acceleration. So I commented on the 8 times force lift, but here's how to specifically calculate it. You would do what's the sum of forces? Force lift is positive and force gravity is negative. Don't forget that is because we are going towards the center, not because we are going up. So at the top up here, both of the two of these would be considered positive because they are both towards the center. Force gravity is away, that's of course why it's negative. And that's equal mass times the acceleration. So to find force lift, that's simply going to be mg, I'm just moving force gravity over and making it mg, plus ma, where a is 7 times gravity, and mathematically you can see here what I said earlier. There's 1g, plus this is, of course, another 7g's, or you'll remember a second ago, that's 68.6 meters per second squared. And that should be, what, 30,000 kilograms times g plus, I'm factoring out the 30,000 here, plus that 68.6 meters per second squared. And we get a force of 1,000 times 9.8 plus 68.6. It is 2,352,000 newtons. Now, as you look at this, there might be other problems that we do with planes that refer to the pilot. And you might look at that force and go, ain't no way a pilot would survive that. You're correct. That is about, to put this in perspective, 10 million pounds. But the pilot, while getting the same acceleration, will not need the same amount of force. Why? Because, of course, they don't have the inertia of a plane that has 30,000 kilograms. So you can do something very similar to this particular setup with the pilot. I would change a couple things. One, that's the mass of the pilot, which would probably be closer to about 80 kilograms-ish. Two, the lift is obviously not pushing on the pilot. It's probably going to be the bottom of the seat. So you would say, in this particular case, a force diagram, instead of force lift, you'd say like seat on pilot, seat on person, or you could even shortcut this, and I'd be fine with you even saying force normal in this case, just knowing that that is the pilot. So that's how you would specifically find this. This, you could see another problem that would reverse this, that would tell you the force normal and force gravity and ask you the acceleration, or it maybe even say, okay, here's your maximum force normal, here's your force gravity, here's your mass, find acceleration, and in turn say like, okay, if this is the radius, what speed can you go? Well, you'd find acceleration, you'd come over here, along with acceleration and the radius, you could find what speed you could particularly go. And that's how to do that problem.